Hello, everybody. Good morning to some of you. Good day to some of you. Good evening. Today, this will be a very interesting, I hope, webinar on the topic of what is tan delta and how do we measure it. My name is Andrei Shepchich, and I'm a regional area manager working in Altanova. And today, through a discussion or through a presentation, which will be about 1 hour long, we are going to find out the basics of tangents delta. You will see throughout the presentation that tangents delta has few other names. One of them is DF, or dissipation factor, and another term used for this is power factor. Now, power factor is not completely equal to tan delta. That name is used in some countries like, let's say, USA, Canada, etc. But we will see also what are the differences. In general, we're going to talk about this concept of tan delta. We're going to talk about insulation, because tan delta is connected with insulation. And for each and every one of you, I want to turn your attention to the handouts section in the right side, in the bottom part of the GoTo application, where you can find this presentation in PDF. You can also find some brochures, and you can find an ebook on how to test a transformer, which is something you might appreciate. So let us start with today's presentation. So the first thing we're going to talk about here is what is tan delta? Well, the tan delta is the most common technique used to assess the insulation of our primary equipment. This can be a transformer, and today we'll talk mostly about transformers, but you can also apply this on a rotary machine like a generator or a motor, or on a cable or on a circuit breaker. Anything that has electrical insulation, you can test it using tan delta. Also, an important thing to emphasize is that this is an AC test. There are also some tests done using the DC method, but today we are going to talk about tests using alternative voltage and current. What is this test used for? It is used to test aging of the insulation and some possible mechanical deformations. We will see how this will be done in the subsequent slides. So when we talk about insulation in general, there are different types of insulation. There is thermal insulation, which keeps us hot in the winter and cool during summer, so it insulates us, it separates us from something. There is sound insulation used in studios, and today our focus will be on electrical insulation. So electrical insulation, of course, because we're electrical people, is what we're going to be we'll be talking about today. And as we talk about electrical insulation, we can separate electrical insulation into solid, liquid, and gaseous insulation. So solid insulation can be cellulose, paper or pressboard, it can be cast resin, it can be porcelain. Liquids can be all kinds of mineral or silicon oils or some kind of synthetic compounds. And gaseous insulations, it's sulfur hexafluoride, SF6, or electrogas, as it is known in some countries, air and vacuum, or nitrogen. So these are some of our insulations, and let's see how IEEE defines an electrical insulation. So what is an electrical insulation? It is a material or combination of suitable non-conducting materials that provide electrical isolation of two parts at different voltages. So let us first discuss the first part, which says material or a combination of suitable non-conducting materials. What does this mean? Well, in this case, it means that we can use one material. As we said, it can be a cast resin, porcelain, pressboard, but often, especially in transformers, we have few different types of insulations. We can have mineral oil and paper, or mineral oil, paper and pressboard, or there can be also porcelain. So it can be one or multiple elements. Now, the second part of the definition says two parts at different voltages. So two parts at different voltages means that on one side we have one voltage, on the other side we have another voltage, and in the middle we have a dielectric, we have an insulator. So what does this remind us of? Does this sound somehow familiar? Two voltage levels and something which is non-conductive in between. Well, that is a definition of a capacitor. So you see, we start this story about tan delta through a capacitor. Why? Well, because the definition tells us so. So let us look at one capacitor, two-plate capacitor, the most simple, let's say, example which we can have. We have conductive plates. In the middle, we have dielectric. Let's say that this is press board, and then we have another plate. They're defined with the area, the distance between them, and the permeability of the dielectric. So what could this be in our world? This can be, let's say, a high voltage and a low voltage winding in a power transformer, or it can be a ground. Let's say this is a ground, or in the stator on a motor or a generator, or it can be a high voltage and ground in the transformer, or it can be low voltage and ground in a transformer. So whenever we have two different electrical potentials and the dielectric in between, we have a capacitor, something that can hold an electric charge. Now, this is not intended necessarily to be in a transformer or a generator, but it's there, it cannot be escaped, and that's why we decided to use this to describe the health of our insulation. So moving on, let us go a little bit more in depth and see how does the formula for a capacitance of a two-plate capacitor can describe to us what are we actually measuring when we are measuring tan delta and capacitance. So we have capacitance in farads, we have permeativity of dielectric, and we have area and the distance between two plates. So we can now observe these three parameters, and if we measure capacitance at one point in time, and then we measure it again after 5 years, and if this number changes, if the capacitance changes, there are a few things that can change. Epsilon can change, which means permeativity change. It means that the dielectric properties have now different characteristic. It means we don't have the same insulation anymore. Or A and D can change. They describe the geometry of the transformer of the capacitor. And if these change, it means that something physically moved inside. And of course, all of them can change. Permeativity and the geometry can change. And in that case, we have, in general, a bigger change than if only one or two of these parameters would change. So this is how this functions. And in order to understand it a little bit better, let us now concentrate on a scheme of an ideal capacitor. So we have here an ideal capacitor charged with AC voltage. And we know that voltage and current are shifted in phase exactly 90 degrees in an ideal capacitor. Current is leading, voltage is lagging. That is because that is 90, exactly 90, because there is no other current running through the capacitor but the capacitive current, because it's an ideal capacitor. Now, if we have an ideal capacitor, obviously there should be a realistic capacitor. And the realistic capacitor is actually something which we will see in the next screen. So we can see here the current, we can see here the voltage, and we can see here the phasors, how are they related. And we will see later that tan delta is actually quantifying the difference between ideal and real capacitor. So the real capacitor is this. The real capacitor has a resistance connected in parallel with this capacitor here. So we do have now some current also running through this resistor, which is very big. It has a huge resistance, mega ohms, hundreds of mega ohms, which means that the resistive current running through here is very small, especially very small in respect to the capacitive current running through the capacitor, but it's still not 0. So it is finite, but it's very small. Another way to explain this is that there is no ideal insulator in the world. Ideal, by that I mean that this insulator will not let through any resistive current. You always have some measurable resistance, and if you have measurable resistance with the applied voltage, you will definitely have some resistive current. So we can say that we are searching for the value of insulation's equivalent scheme. We have capacitance, we have resistance, and the tan delta is a physical reality that connects these two elements. So by measuring capacitance and a large resistance, we are measuring tan delta. We are basically measuring how non-perfect our insulation is, and we have modeled our insulation with a capacitor, and then to make it more realistic, we have modeled the capacitor not as an ideal but as a realistic capacitor, and the realistic capacitor has resistance and capacitance. So how do we measure these parameters? In order to measure these parameters, we have to generate some voltage here, and that voltage is generated by the device we use to measure this. And after we generate the voltage, we measure the current which is passing through this equivalent scheme. What will be very important is the phase shift of the current. The phase shift in respect to the voltage that we generate will make all the difference, and that will actually tell us how much is this and how much is this. So, of course, since we have here the capacitive current and the resistive current, we will be more interested, let's say more interested, in this resistive current. Now, why are we more interested in this resistive current? Well, because when we talk about losses, and let's be honest, I mean, we are testing our insulation to see what our losses will be. We know that the formula for losses is voltage times current times cos phi. Cos phi for resistive current is 1, so we have voltage times IR. So let's take an example. If we have a high voltage asset and we have it on the network, we can have a very big voltage, 132, 220, 66 kilovolts. And if we have only 1 milliamp of resistive current in this insulation, which is really not much, for example, the power which is generated is 10 watts. Now, this is just an example to show you how much energy can be lost. So 10 watt in 1 hour will be 10 watt hours, but even one day it will be 240 watt hours, in a month 7.2 kilowatt hours, and in a year 86.4 kilowatt hours, which is worth about 15 euros in today's prices of electricity in Europe. But actually this is not the issue. The issue is that it's not just a financial loss. The biggest issue is that all this energy is turned into heat. And this heat is what tends to destroy or degrade our insulation. So the heat which is being generated here has to be removed. So we need to remove that heat using all types of coolers, fans, pumps, oils, etc., etc. So in order to do that, so that we don't have a problem like this poor transformer has, with this heat, which is constantly being applied on the insulator starts to degrade, which as a consequence has an increase of the resistive current. So the resistive current will now increase, but as the resistive current increases, more heat will be dissipated, which will in return damage the insulation even more, and it will allow more current to flow, and so on and so on. So bigger resistive current, bigger losses, bigger degradation, bigger resistive current, bigger losses, bigger degradation. So it's a vicious cycle, and it's a chain reaction until the insulation completely breaks and sparks start flying. So in order to avoid something like that, we need to understand in which point is our insulation. Okay, so this part was a little bit introductory and technical. let me now give you a short story how insulation in any aspect can be taken, or how the testing of insulation can be important. Now, this is a story of Hans Brinker. It's a Dutch story from Netherlands. It's a story about the boy who saved his village. So in Netherlands, you know that big part of Netherlands is below the level of the sea. You can see that example here. This is the sea and this is below the level of the sea. So obviously you have dikes, insulators, which insulate them from the sea. So who was Hans? Hans was a young boy coming back from the visit to his sick grandfather, and while returning, he saw a leak in the dike. There was a little bit of water splashing out. So all kids, as well as grown-ups in Netherlands, know that if you see a leaking dike, you should put plug in that hole and you should do it fast. You should plug that dike. Why? Because when something is coming out, you don't know what's happening inside. So the smallest visible leak might signify that inside you have a lot of problems, and if you let that water flow out, you will increase that problem. So stopping that was very important. He plugged that leak, as you can see here, with his finger, and he kept on calling for help. He shouted whole night, and in the morning, luckily the priest, who was passing by on a bicycle, saw him. Hans was exhausted because he was there all night trying to plug that hole and calling for help. So the priest took him, he was freezing, and the villagers relieved Hans of his duty and helped him to get, a little bit warmer. And that's the story how the boy saved the village, just by pushing a finger into a hole which was in the dike. So to clarify, tan delta is not Hans Brinker. We cannot plug the hole, but we can understand how big the hole is. We can understand how much resistive current is flowing in our insulation and heating it up. It helps us to understand how functional or how deteriorated is our insulation. So this story does inform us how a nonlinear the process of insulation loss is, because a small hole of only a few centimeters in diameter can very quickly destroy the whole dike. The same way, a very small resistive current can cause an insulation deterioration and the short circuit in power transformer, where all distances are very small and with very narrow margins. So we are basically checking on our insulation because of very nonlinear characteristic of the insulation, because a very small current might suddenly become a very big current, which can very quickly destroy the insulation of our primary equipment. Now, there is another way how to tell this story. You see, imagine yourself in front of an aquarium with no fishes but a working TV set inside. It would look confusing because you would think, okay, how can a TV work inside of water? But then let's say you realize that it is not water, that it's a mineral oil, which is normally used in transformers. And since it is a transparent liquid, you wouldn't see any difference. So you're sitting in front of an aquarium which has a TV inside, and inside you have mineral oil. Since mineral oil is insulating, you could watch TV, you can change channel, and nothing will happen because there are no short circuits happening. But if every day you drop one droplet of water inside and stir it up, first day that droplet of water will not make a difference. The second day, probably not. The fifth day, probably not. Maybe even the 50th day, nothing will happen. But on the 100th day, maybe there will be enough water inside that mineral oil to start making it more conductive. You see, this is a story which describes how the oil inside our power transformers, which has very little or no water molecules inside, can draw water molecules from the air when it's breathing, because the transformer breathes, and thus create not an insulating compound, but a slightly conductive compound, which can then help to create a conductive path and create a short circuit. So tan delta will measure for you when is the time to change the oil in the transformer, or when is the time in this case to take the TV outside. So finally, why do we test tan delta? We want to know the state of our insulation, or from the insulation breaking. Since insulation has a very nonlinear characteristic, a very small increase in resistive current can suddenly make the insulation break. And it is important to say that high value, if not too high, is not necessarily a sign that we need to change the asset. Often, we just need to follow the trend of the tan delta and act if the change is too big. So by that, we mean that we do have some numbers which describe the maximum allowed values of tan delta. But sometimes if the increase is very slow, you don't need to rely on the number itself, you need to rely on the trend, which is very important when assessing. Trend in general is very important when assessing the state of any electrical insulation. So in order to keep the asset running, test tan delta. So in this first part, we answered the question, what is tan delta and why do we test it? Now in the second part, we're going to talk a little bit about theory and practice. Now I forgot to say, if you have some questions, feel free to ask them in the questions section. We will reply in the end of our presentation. I see that some of the attendees are having issues with hearing my voice. I suggest you try to disconnect and reconnect, because in general, I have information that the voice is heard. Now let us proceed with capacitance and tan delta theory and practice. So in the theory and practice of tan delta, we will show you some of the devices which we use to do a tan delta measurement, capacitance and tan delta. We see here STS and the TD5000. So let's see how some vectors and how of current and voltage in the insulation help us understand how to measure tan delta. We said before, ideal capacitor has 90 degrees between the current and the voltage which is causing that current. So this is 90 degrees, and in that case, the resistive current is 0. But in a real capacitor, we do have some resistive current passing through this resistor. Now, in our case, the total current is capacitive current plus resistive current. So this is the charging component and this is the loss component. And we said that IC is much bigger than IR. But regardless, the IR is not 0. And even if it's small, multiplied by the high voltage here, we get losses, we get heat, which needs to be removed. Otherwise, it deteriorates our insulation. What we have done here, we have drawn a graph. We have drawn the capacitive and the resistive current. Now, keep in mind that in this case, in order to illustrate this problem, we have drawn a very big IR. Even though IR, the resistive current, is not this big, it is much, much smaller. We have tried to show that right now, the total current is not at 90 degrees, but it's at a different angle, which is less than 90 degrees. In practicality, this angle will be maybe 89.5 or 87 degrees. So this line will be very close to the y-axis. Excuse me, very, very close. But still, it will not be the same as IC. So let's see. How do we define tan delta? Very simple. Tan delta is the ratio of in-phase resistive current and the 90-degree capacitive current. That's it. It's as simple as that. And this is the angle delta, and the tan delta is this current divided with this current. We can also say that if we multiply this with the same voltage or express ourselves in the admittance and resistance, the tan delta is 1 divided by omega RC. So you remember when we were saying that we are looking for the equivalent scheme of our insulation, we were looking for the R and the C and the omega, which is 2 pi frequency. So we can calculate in both ways. And in our case, what we do, we generate voltage, we measure current, and then we calculate tan delta. One important thing to say, which we mentioned in the beginning, is the tan delta is also referred to as dissipation factor, or DF. In some countries, the tan delta is referred to C and DF, capacitance and dissipation factor. Somewhere we just say, in some countries, tan delta, and sometimes we say power factor. We will see what is power factor right now. So once again, this is the angle we are looking for, actually the tangents of this angle. This is the resistive current, this is the capacitive current, and in general, this is the total current, which is very close to the y-axis. Now, we also use the term power factor. The definition of power factor is somewhat different, but I will just say that up until 10 degrees of delta, tan delta can be considered the same as power factor. What's the difference? Well, the power factor is IR over I total, while tan delta is IR over IC. But if I total and IC are very similar, and we were saying that this total current is usually very close to the y-axis, then we have the same number. So we can also say that if tan delta and power factor are different, then the insulation is already compromised due to the fact that the angle is too big or too high. Keep in mind that this angle, we said 10 degrees, this is the angle we're talking about, usually is not bigger for a transformer than 0.5, maybe 0.6 degrees. So 10 degrees is 10 times bigger, 15 times bigger than what we've expected. Sometimes for generators and motors, this angle can be a little bit bigger, maybe 3, maybe even 5 degrees, but not as big as 10 degrees. Of course, we can recalculate power factor and tan delta using these formulas, which you can see here, power factor and tan delta, but in general, these numbers are almost the same. If they are not, we already have a problem with insulation. So how does the insulation get compromised? Well, as the time progresses, insulation, for example, in a power transformer, gets older due to the inherent processes in the primary equipment. For the power transformer, it is because every transformer breathes. It breathes because the volume of oil during the day, since the transformer works more, is bigger than the volume of oil during the night. So something increases during the day, the volume of something, like you breathe in, and then during the night, you breathe out. So you have air coming in through the breather and air then coming out. The air has water molecules inside, and this water, even though there is silica gel, which you should change regularly, some molecules of water do get inside. Also, due to partial discharge and some other processes, gases like thermal are developed, which increase the conductivity. If you have partial discharge, you will have more hydrogen. If you have hot spots, you will have some other gases, ethane, methane, etc. And all these gases, also when they're diluted in the oil of a transformer, can increase the conductiveness of the oil. Also, certain oxidation processes create the sludge, which gathers at the bottom of the tank, and it also reduces the insulating properties of the oil. So all these parameters, so breathing of the transformer, partial discharge, heating inside, hot spots, and oxidation processes, they decrease the insulating properties and increase the conductivity of the transformer. And then we need to know what are the acceptable values for a transformer when we measure tan delta to say that the transformer is good, has a good insulation or a bad insulation. So let's start. Here we use the values measured at 20 degrees Celsius. The DF or tan delta for a new transformer should be less than 0 or equal to 0.5. So this is 0.5 for a new transformer. For a service age transformer, the tan delta or the DF has to be below 1%. We will see in the next graph, in some cases, even less than 1%. But in general, 1% is a rule of thumb which is applied on most of the transformers to say that the values below that are good values for the insulating properties. If we have more than 1%, then we should do some further investigations. Further investigations means that we can do a voltage sweep, for example, on the body of the transformer, or we can do a frequency sweep on a bushing of the transformer. So all these things can be done, including, for example, additional tests of the oil, maybe partial discharge test, we can do in order to see what is the real problem with our insulation. So here, what we see is the fact that not all types of high voltage or medium voltage transformers have the same tan delta. First of all, if we have a higher voltage transformers, 220, 400 kV or 132, we will see that the tan delta needs to be lower than 1%. Still, it needs to be much lower in some cases, but never higher than 1%. We can see that here. And another thing, when we measure tan delta, we also measure, as we said, the capacitance. We measure three parameters. We measure the capacitance between the high voltage and the low voltage winding, the high voltage winding and the tank, and the low voltage winding and the tank. And we can see that the high voltage, low voltage in this case, this case, this case, and this case have to have the lowest values. So high voltage, low voltage is the most important insulation. And you see that in the first case is between 0.2 and 0.5, while in the case of 66 to 11 kV transformer, it's between 0.3 and 0.6. Of course, it can be even below 0.3. For 132 to 11 kV is between 0.3 and 0.6, but for a distribution transformer, it is between 1.5 and 1.8. We can also see that high voltage and low voltage can have a slightly, say that with our test set, you can go even up to 9 nanofarad. But with this one, we can measure, these are the standard capacitances. So these are the values, let's say 1% and below would be the standard value of a tan delta when we measure it on a power transformer. For rotative machines, as we mentioned, sometimes 3, sometimes even 5%, depending on the type of insulation. So this is, now we talk about how we evaluate the results we've got. Of course, we can say that it has to be always below 1%, but sometimes a simple comparison is also a very good indicator, because if we are around 1% and it increases slowly, it's not a big problem. But if it increases quickly, then it could be a problem. So what is a slow increase? What is a big increase? Let's say that the change should not exceed 0.1% per year, or even less. So comparison with previous values measured from the same transformer. Then we compare to the allowed values. For example, we check this table. Or often when we do, let's say 3 bushings, when we measure each bushing and its tan delta, we can compare the phases. They need to have the same value. If one of them has a higher value, we should investigate that. And then we can also do the comparison to the same type of a transformer working in similar conditions and having the same age. So these are the ways how, when we get the number, we can say, okay, it didn't go up too much from last year, or it's still below 1%, or in comparison to other phases, it is the same. Or if I have a similar transformer, we can say, okay, it has the same values as this similar transformer, which is working in the same conditions and has the same age. Let us turn our attention also to the fact that the frequency and the voltage has to be standardized. Standardized, by that I mean that we do not have to measure with the voltage value bigger than 12 kilovolts. I know this might sound strange to somebody, but 12 kilovolts is the voltage at which polarization has fully taken its course, and you don't need to go higher, because even if you measure with a higher value, you will not get different results. Very often, even 10 kilovolts is used, but you also need to keep in mind that when you're doing this measurement on the transformer, the value should never exceed the nominal value of your primary or secondary side. So if you have 10 to 0.4, when you generate on the secondary side, you will never go more than 0.4 kilovolts. So 400 volts. So this needs to be also very clear. Frequency, which we use, is nominal frequency, 50 or 60 hertz. Sometimes maybe 0.5 or 1, maximum 2 hertz, you can go and change a little bit, because we have seen that the tan delta does depend on the frequency, but not too much. For rotative machines, sometimes we can go a little bit more, 3 to 5 or 4 hertz lower or higher. But for power transformers, we want to be as close as possible to the frequency. Having said that, keep in mind that we actually never do a test exactly on 50 or 60 hertz. We always do it at plus or minus 0.5 degrees, or plus or minus, 0.5 hertz or 1 hertz, in order to avoid noise. You see, we are measuring very low currents here in the range of milliamps, and the phase shift between that current and the voltage which causes it are very small, like 0.5 degrees. So we are trying to be not to be on 50 hertz and not to be affected by the noise. So here you can see some of our test sets, the STS and the TD5000. The TD5000 is an accessory for tan delta, and also the TDX5000, which is a single device used to test tan delta. They both generate up to 12 kilovolts, the maximum of 300 milliamps, which is more than enough, because you would normally generate maybe up to 10 or 20 or maybe 30 milliamps when testing a transformer. When testing a cable or when testing a generator or a motor, that can be more. And let us repeat once again on which assets we can test tan delta. First of all, we can test it on a power transformer, on the body of the transformer, and on the bushings of the transformer. We can test it on instrument and transformers, like protection and measurement transformers. On generators and motors, we do a tip up and a tip down test. We go up and then we go down, and we want to see the same values. On cables, on circuit breakers, and also on surge arresters, where we use a watt loss measurement. Also on circuit breakers, we mostly use watt loss measurement, and these are some of the most important primary equipment, and on all of them, you can do a tan delta test. So moving on, let's see what is the standard procedure when we want to do a tan delta test. First of all, on the power transformer, let's say. First of all, the transformer needs to be removed from the network. Of course, this is an offline test. Then we touch with the grounding rod all phases on all sides to be sure that we have completely de-energized the transformer. Otherwise, if we don't do that, then some current might be discharged in the test device, which might not be a good idea. And then we need to short circuit with a thin wire. We need to short circuit the primary side, and then separately the secondary side, and if we have also the tertiary side. Now, when we have done that, we have created 3 potentials. Or if we talk about primary and secondary side, we have created 2 potentials, the primary side, the secondary side, and there is also the ground. Then we need to ground the test sets properly. This is a very important thing, because we measure the grounding current very often. And if we have STS and TD, the STS, TD, and the trolley need to be grounded in the same point as the transformer that we are measuring. So we see here how we need to do that. If we have a power transformer, the primary side, the secondary side, they are all separately short-circuited, thus creating a single potential. And then we are measuring the CHL and the tan delta between the high and the low voltage side. we measure the CH, capacitance between the high voltage and the ground, and the tan delta of that, and the CL, the capacitance between the low voltage and the ground, and the tan delta of that. So CL, CH, and CHL. Now, how do we physically connect the generation and the measurement? The high voltage side in our first step will be connected to the generation will be connected to the high voltage side, and the measurement will be taken from the low voltage side. And in this setup, we can measure CH and we can measure CHL. So the capacitance between the high voltage and the ground, and the capacitance between the high voltage and the low voltage winding. Then we go to our firmware. In the nominal values, we say 2 windings transformer. We punch in the nominal power, the primary and the secondary voltage, and off we go and to the firmware for tan delta measurement. We made this firmware very user-friendly. The only thing you need to do is in this drop menu, you need to say where have you connected the generation of the device, to the high voltage side or the low voltage side of the tertiary side of the transformer. In this case, we are connecting it to the high voltage side. And in the second drop box, you need to say which capacitance you want to measure, CH or CHL or something else. Automatically, the method USTA, this is something which we're going to talk in our next webinar next Tuesday, the advanced tan delta. And you don't have to think about this, it is automatically chosen. You choose the voltage, the frequency, and if you're not sure how to connect, you can always press the question mark button and you will get the scheme as you saw in the slide before. So we need to position correctly the cursor and then press start. We observe the left corner, lower left corner, to see the stages, calibration, measurement, and when it's done, you will see test is done. The test takes about 30 seconds, after which you can see the results. Now, after measuring the CHL, we change this to CH, as we said, so we now choose CH and press the start again and check the results. We press the emergency button as we approach the power transformer. This is a good practice to be sure that nobody accidentally presses some buttons on the test set. So you press the big red button, you approach the power transformer, and now we do a change. We change the generation from the high voltage side to the low voltage side, and we change the measurement from the low voltage side to the high voltage side, and it looks like this. So now we are generating on the low voltage side, and we are measuring from the high voltage side. Why are we doing this? We are doing this because in the past, in the previous 2 steps, we measured CHL and we measured CH, but we didn't measure CL. We could not have measured CL with the generation here and measurement here. That's why we needed to switch. Now the generation is here and the measurement is here, and we can measure CL. Of course, with this setup, you can also measure CHL and compare that measurement to the previous measurement when the generation was on the high voltage side, just to be sure that the device is measuring properly. So now, to measure CL, we say low voltage winding is the place where we are generating the voltage. We want to measure the CL. As you can see, we can also measure CHL and CL plus CHL. The device automatically chooses the correct scheme, GSTGA, grounded specimen test, guard A, and we press start. We look at the bottom left corner to see if all the steps, calibration, measurement have been done. And when this is over, we press the emergency button as we approach the PT for the safety reasons. At this point in time, we need to remove the short circuit from the high voltage and the low voltage side, because in the next step, we are going to measure the tan delta on the bushings. And for the bushings, of course, they cannot be short circuited because we measure for each phase at a time. Phase A, then phase B, and then phase C. How do we do that? We need to have a test plug. We need to have a tap adapter on the bushing in order to measure that. Often you will need to unscrew something in order to connect the measurement or the generation, you will often be able to see on the plate just above the values C1 and C2. I will show you what is C1 and what is C2. If you don't have this, you can also use a hot collar, which is like a belt which you wrap around the ceramic, around the bushing, but in that case you need to clean it very nicely, and in that case the interpretation of the results is a little bit different. In that case we rely on the comparison between phases. So this is a bushing, this is a tap adapter, and then we generate on the high voltage side and we measure on the low voltage side in order to measure C1. So this is the capacitance between the top and the tap adapter. After doing so, we switch and we generate on C on the tap adapter and measure from here in order to measure C2. But let's see that in steps. So measure C1 and then C2, and be careful when measuring C2 not to generate more than 1 kilovolt. Actually, there is a safety feature. If you try to generate more than 2 kilovolt, you will get a warning sign, because generating so close to the body of the transformer might be risky. So 1 kilovolt, I would say, is more than enough. We repeat that process for phases B and C of the bushings, and then if we have the low voltage side with tap adapters, we can also do that. If not, we can just leave the low voltage side. And then we move on to the next transformer. And now we have results. When we finish, we have the capacitance CH, CL, and CHL, and also, of course, the tan delta for these capacitances. These define the body of the transformer. Capacitance between the high voltage and the ground, the low voltage winding in the ground, and the capacitance between the high voltage and the low voltage. All of these tan deltas need to be below 1%. If they're extra high voltage transformers, then even lower. For bushings, we will have C1 and C2 for all 3 phases. And if we have also on the low voltage side bushings, the tap adapters, we will also have values C1 and C2 for all these bushings. So all of them need to be less than 1%, as we said before, which is very important. And in fact, sometimes if they're not, as we mentioned before, we want to do a sweep. And the sweep means, for example, if CH is or tan delta of CH is 1.2, then we will do a test at 0.4, 0.6, 0.8, and 1 time U nominal. And we will see how the tan delta changes with the change of voltage. If the same thing we want to do on the bushings, then we will sweep the frequency. Not just 50, but 15, 30, 45, 50, 60, 75, 100, 200 hertz in order to see if this is a straight line. We actually want to see a straight line. We don't want to see that the tan delta falls down and then increases again, or goes very quickly up and then remains there. We want to have a steady linear increase or decrease, no sudden changes when we do this. And also sometimes with measurement, we can measure the sums, CH plus CHL or CL plus CHL, also to verify the accuracy of the device. Because to be honest, in some of the procedures, it is defined that you need to measure CH plus CHL from the primary and then the secondary side, just to be sure that it functions normally. In our case, you will simply, when you are doing a test, choose first CL, do a test, then CHL, then do another test, and then do CL plus CHL, and that's it. So these are the results, and what I wanted to mention is one important thing. When you measure tan delta, you don't just measure the state of insulation of one element of your transformer. You measure the state of insulation of the whole insulating system. You measure the state of the pressboard, all the cellulose, the oil, everything is connected, everything is put into this one number. You know, this is good because if you measure just one element, for example, oil, and you find out there is very little water in the oil, you need to keep in mind that most of the water which is inside the transformer is actually in the paper board and in the in the cellulose, and you cannot reach that. So you might have a wrong conclusion if you test the oil and see not a lot of water inside. That water could be hidden in the cellulose, and often it is because it's more hygroscopic. It attracts water molecules more than the oil. So the good thing about tan delta is that it measures a state of the whole insulating system, not just one component of the insulating system, and then you can have a better overview of the state of your insulation. Now, I also need to talk about element, which is definitely the compensating factor. So the compensating factor means that the temperature does change the tan delta. You see that the same value of tan delta at 20 degrees is 1, and at 70 degrees is 3. So this is also something which is incorporated into our test sets. You need to write the temperature of the oil in order to recalculate the tan delta which you measured to 20 degrees. And then the formula is very simple. The tan delta is divided with K. So as we wrote here, if you measure at 70 degrees and you get 3, this is like you were measuring at 20 degrees and you got 1. So keep that in mind. It is also an important thing. So here we have one example of the report on the transformer which we measured in Kazakhstan. The numbers are very small, but we have in the next slide them explained a little bit better. This would be an example of a result. So here we measured CH at 10 kilovolts and 50 hertz, and we see that the current which was actually generated is just 12.85 milliamps. We said maximum is 300. The capacitance which we measured is 4.0976 nanofarad, and the tan delta is 0.2283. So this is much less than 1%, and this is very good. In the next step, we can also see that there are some other parameters. Let me just go back. You see here, by the way, that tan delta and the power factor have the same numbers, and RP is 342.7 megohms. What is RP? RP is, as we were mentioning before in the equivalent scheme, the resistor connected in parallel to the capacitor. So that's RP. And if it's so big, it means that we have a good insulation. I don't know if you remember, but there was an alternative formula to tan delta, which is 1 divided with omega RC. If you were to take these numbers, 4.0976 nano and 342.7 mega, you would get 0.22 as 0.2283% for tan delta. Of course, there are some other parameters here to look at. The last parameter is the one I particularly like. It's the phase shift. So this phase shift in this particular case for this measurement was not 90, that would be ideal. It was 89.8692. So the difference between 90 and 89.8692 is the angle out of which tan delta is 0.2283. If we play a little bit with these numbers, we can understand that if we say that 1% is the maximum tan delta, which means that we have a good insulation, what would be the angle of that tan delta? And the number we get is 0.58 degrees. So for 0.58 degrees, the tan delta is 0.995. For 0.59 degrees, we have already a number above 1%, which means that we should take care of that particular insulation. There are some other parameters here, like QF. This is basically reciprocal value of tan delta, and it needs to be bigger than 100. In our case, is 437. And RS would be the equivalent resistance in series to that resistance in parallel, and it is calculated by multiplying tan delta with 1 divided with 2 pi FC or omega C. So this is how we interpret the results when we do a tan delta measurement on a power transformer. And before we finish, I hope let us check if we have some questions. So we're just about here to, let's see, let us see. Mr. Nadaf Ashraf is saying, can you explain the difference between capacitance result and tan delta compared to DC insulation resistance? Is it the same capacitance? Well, not really. There are some other elements happening when you do an AC test. In general, why we don't use the DC method? We don't use the DC method because the repeatability of the measurement is not that good. That's one thing. And another thing, it is proven that the DC method leaves a lot of electrons inside the asset. And if you had some voids in the past, now these voids have free electrons and they can trigger a partial discharge activity. So this is why we don't use the DC method. Okay, we had some problems in sound. So Mr. Enrique is asking, does the STS 5000 come with the computer control software, or every measurement has to be making with the little screen of the device? Of course, you can use the computer. That is a possibility. In that case, there is a license and you can start the test and stop the test with the computer. That is completely valid and you can do that. I personally prefer using the local little screen, which is actually not so little, because it is more comfortable. It is, let's say you don't have to carry around with you another device like a PC. So you can do it both ways, with the PC or without the PC. In some cases, when this is installed in a van, and when we have in the van a lot of testing equipment for a transformer, then it makes a lot of sense to do that from the PC. So I hope this answered your questions. Mr. Nadaf Ashraf was asking, there are standards for tan delta results. As we shown, let's say 1% should be maximum for power transformers, in some cases even less. Also the delta, the change of tan delta shouldn't be too high. So these are the standards when talking about tan delta. Mr. Yabid is asking, how do we analyze good or bad tan delta measure for equipment without having any data of the equipment for previous tan delta measurements? As we said, I think before 1% is more or less what we have. You can download this presentation from the handout sections and see, depending on the type of the voltage of the transformer, the voltage level of the transformer, sometimes this value needs to be even lower. But the suggestion is that start testing your transformers regularly, and that way you will be able to create a database which will give you a much better overview. Trending is very important when it comes to assessing the state of insulation or of primary equipment. So if you can trend or do a measurement in time, that would be the best solution. Mr. Muhammad is asking, in this case, 2% is allowed for distribution transformer. Yes, in some cases, 2% is allowed. You see, sometimes for a new distribution transformer, even 0.7 or 0.8 is allowed, so 2% should be okay. What is important is if you can do, and with our device, you can do the sweep with the voltage, and if you don't see any changes, if you don't see any non-linear changes, it means you have a good insulation. Measuring, so Mr. Branko Čulić, how about measuring tan delta on dry transformers? Absolutely. You can do it on a dry transformer, you can do it on an oil-filled transformer. Any transformer can be, you can have a measurement of tan delta on. It doesn't change in any way. It's simply that a dry type transformer probably will be a distribution transformer, and in that case, the interpretation of the result would be less conservative, so you could have a bigger changes, a bigger value of tan delta in when measuring, in order to tell you that you still have a good insulation. Mr. Haider is asking, for 400 kilovolt, 400 to 200 kilovolt, high voltage to low voltage, DF should be 0.2 to 0.5%. For 11 kV high voltage, low voltage is 1.5 to 1.8%. Does this mean we can have more DF for a low voltage system? Yes, it means that if you have a higher voltage, you have stricter rules. It's like if you have a higher voltage, there is a higher propensity for a fault because the stresses are bigger. And in that case, it's like having different rules for, let's say, pipes who can have a small leak or a bigger leak. If you have a bigger pressure in the pipe, the maximum leak you could have will be much smaller than the leak for a pipe where you have a lower pressure, because if you have a higher pressure, you know that even a small leak can create havoc. And if you have a lower pressure, the leak might be even a little bit bigger and it will not create such a big problem. So the voltage level definitely is a parameter when assessing the tan delta, the same way like for partial discharge. If you have 11 kV cables and you have a certain amount of picocoulombs or millivolts, then it might not be a big problem. But if you have that same amount of millivolts on a 220 kV cable, it can soon create a problem because of the bigger stress. Mr. Sebastian, for this measurement, do you have a method to perform these without disconnection of bushing and high voltage cable? Because in exploitation, disconnection of high voltage cable is complicated and we have to change bolts and unscrew. Thank you, sir. Well, to be honest, no. But we have a solution, which is monitoring. You see, if you want to do a tan delta test, you need to generate voltage and you need to measure the current. So you need to disconnect. But in this case, which you are describing, I propose continuous monitoring of tan delta. That is something we also provide. You put sensors in the tap adapters, or you can even put at the same time the monitoring of partial discharge. And then you have a trend of tan delta and partial discharge, which will tell you exactly what stage is your insulation in. So for this case, I propose installing the monitoring solution. Mr. Haider, what are tip up and tip down tests? The difference. The tip up test is when you go from, let's say, 0.2 to 0.5 to 0.7 to 0.9 to 1.1% of nominal voltage. And the tip down test is the same thing, but going down. 1.1, 0.9, 0.7, 0.5, 0.2. You do those tests on rotary machines to go up and then to go down in order to see that the tan delta is the same for all of the values. I mean, not for all of the values, but for the same voltage levels when going up and when going down. Mr. Enrique, with an output of 300 milliamps, what is the maximum cable length you can test? That's a good question, but that depends on the type of the cable. Usually we would say maybe a few hundred meters, surely 100 or 200 meters for, let's say, 6 to 11 kV cable. We cannot say exactly because, as I said, the capacitance of a kilometer of a cable depends on the type of the cable. So it can be bigger, it can be smaller, but until now we managed to test at least up to 1 to 200 meters of medium voltage cable. So the smaller the capacitance per kilometer, the longer the cable you will be able to test. In some cases, maybe you could also use the reactors, which are the devices usually used to test tan delta for generators and motors, and increase that to even bigger length. So that is possible, because when we are testing on generators and motors, we need more than 300 milliamps. Sometimes we need 1 or 2 or 4 amps, and then there is a reactor, which is basically the winding, the inductance, which takes over, which creates, together with the capacitance of a rotary machine, a resonant circuit, and then you can generate a bigger current. Mr. Asfav, what is the degree of taking tan delta test results in order to take measures? Can you mention what are the things to be checked for confirming the results? What are the critical issues when we are suspicious about results? So if I'm understanding this correctly, as we mentioned before, 1% should be what is the critical value, more or less, depending on the voltage level. And apart from that, if you're not sure, we do a sweep test to be sure that the insulation is good. Of course, it would be good to do this measurement, let's say every 1 to 2 years, depending on how important your asset is or how important your asset is de-energized to do this test. In general, this test doesn't take more than half an hour to be done because the measurement is quick. You don't have to wait for anything. It's just the connections, connecting and disconnecting. One important thing I wanted also to tell you when doing this test. When you're doing this test, especially when you're generating high voltage on any of the sides, the cable which brings high voltage shouldn't be touching anything, because in that case, sometimes you might have, due to the stray capacitance, excuse me, you might have some issues with generation. So the cable which brings the high voltage to the testing point should not be touching anything. Mr. Sebastian Gasco is asking, does this test more precise than oil analysis? Well, yes, because it tells you the state of the overall insulation system. For sure, in that case is more precise, but oil analysis might give you some data which tan delta cannot give you. Oil analysis will tell you how much of which gases you have inside oil. Tan delta cannot tell you this, but tan delta will tell you how are the good insulating properties. How good are the insulating properties? And in the end, you want to know if the insulating properties are good or not. The oil test can also tell you what might be the reason why the insulating properties are not good. If you have too much hydrogen, then it could be the partial discharge. If it's too much acetylene or ethylene or something like that, it can be a hotspot or something like that, and it give you the reason. But that tan delta tells you if it's insulating or if it's not insulating. So in that case, it's more precise because it doesn't check just the oil, it also checks the state of pressboard, the cellulose, the paper, etc., etc. And you need to know that. Otherwise, if you don't, you might think that the oil is perfect and basically you have a lot of water in your cellulose. Mr. Kelvin, how superior is the STS to the conventional ground tester when it comes to TX insulation testing? I'm not sure I understand that question, Mr. Kelvin. Can you elaborate a little more? How superior is the STS to the conventional ground tester when it comes to TX insulation test? Please do elaborate a little more. We'll move on to the next question. Mr. Sharif, how do we make the test set up for rotating machines and interpretation of the result? We will cover that in some of the subsequent tests, but in general, you are doing this. If you have the chance to separate each phase one from another, so phase A separate from phase B, separate from phase C, then you can test each phase versus ground. By the way, when you're doing the motor or generator testing, then you are testing the stator winding versus ground. So that's the first stop. Can you open the star and can you test each phase versus ground? If not, then you test all three phases connected together versus the ground. You generate on the phases, you measure from the ground, you do a tip up and you do a tip down test, and you see if the tan delta is below 3 or 5%, depending on what is the type of insulation you guys have. And sometimes you just need to do a tip up and a tip down test and not even look at the numbers so much. But when I say look at the numbers, compare them with some values, you need to see if on the same voltage level, they are the same when you are going up and when you are going down. Mr. Astraf, why tan delta at 50 Hertz is preferred? Why tan delta at 50 Hertz is preferred on VLF? Oh, to be honest, we don't do a lot of VLF, so I really cannot answer fully that question. I don't want to give you any information which are not correct, but we prefer doing tan delta at 50 Hertz because that is the working frequency, or 60 Hertz of an asset. And you know that if you do it on your nominal voltage or nominal frequency, then you get the most realistic results. Mr. Muhammad, does your test set has the option to measure tan delta for transformer oil? Yes, it does. So for transformer oil, you would use a special accessory called Stoil cell. It is a metallic cell where you put in some of the oil, about between 0.7 and 0.8 liters of oil, and then you connect high voltage, and again you go up and you go down with the voltage to see what is the tan delta. So you do a voltage sweep. So yes, that option exists. Mr. Miloš Sušić, can you tell us more about the experience and measurement tan delta on surge arresters? Well, on surge arresters, basically what you need to understand is if the surge arrestor is functioning properly, in a sense that its resistance is where it should be. So the dissipation of power is not too big. The current which is passing through a surge arrestor shouldn't be too high when the nominal voltage is on the line. So you would do the same thing. You would generate your voltage on a surge arrestor, and then by using you would need to have some kind of either previous values or a table, or talk to the producer of a certain surge arrestor to understand what is the nominal power consumption of your surge arrestor in order to be sure. I would propose, when we're talking about surge arrestor, another test set called SCAR-10. SCAR-10 is a very simple test set, and it basically does this. When the surge arrestor is working, you put the current clamp around the grounding wire and you measure the 150 or 180 hertz, so the third harmonic of your of the leakage current, and by measuring that you are able to say if your metal oxide surge arrestor is functioning well. It's a much easier and also cheaper method to do. Mr. Al-Shamsi is asking, how far the benefits of the IR test compare to tan delta, and what is the tan delta for 33 to 11 kV transformer? Well, IR, if you mean infrared, if you mean temperature, will give you some ideas if you have any hotspots. Having hotspots can cause the development of certain gases which can increase the conductivity. So these are complementary methods. You cannot basically use one and not use the other. It's like if you go to a doctor, he can use a stethoscope to listen to your lungs and to listen to your heart, but then he can also take your blood and do the analysis. They're complementary methods. You cannot normally compare them. And when we talk about 33 to 11, the nominal values, I would always stick to 1% to be sure, maybe even 1.5 in this case. If you are not sure, do the measurement today and then again in a year, or do a voltage sweep today and see if you have a straight line going up or going down, or this line suddenly increases and then decreases. So this would be for Mr. Al-Shamsi. Mr. Godfrey Kingu, if the oil temperature of the transformer under the test has, say, 40 degrees Celsius, is it opposite to put in this data during test and equipment converts? Yes, correct. The equipment, if you use, you see here we have the tab temperature compensation. It is here, and when you click here, of course now I cannot click. If I do, I will change the slide. If I click here, then it will ask me what is the temperature of the oil, and it will automatically recalculate. Excuse me. Let's see if we have some more questions. Mr. Andres Alvarez, hello, which voltage should be used if we want to measure CL for a low voltage winding 400 volts? The nominal, not higher than that. And also be careful. So you will short circuit the low voltage side and you will generate 400. If you want, go with a lower value, go with 200, go with 300, and see if the value changes. It shouldn't change much, but don't go too much higher. You can go maybe 10 or 20% higher than the nominal voltage, because we don't generate voltage for a long period of time. It's maybe 5 to 10 seconds. But still, especially if it's an older asset, don't go higher than the nominal voltage. So 400 volts should be the correct answer. Mr. Arshad, can we do tan delta test for GIS or HIS system? It can be done, but it's not that common because you cannot find places to connect to. So in my experience until now, I have not done anything like that. I heard that theoretically it could be done, but I wouldn't actually know how to do that. For a GIS, I would propose partial discharge test. Partial discharge test will tell you much better at which stage the insulation is, because it will detect the possible electrical discharges inside of your GIS. Mr. Muhammad is asking, for a 40-year age distribution transformer rate at 6 kilovolts, what is the recommended maximum test voltage? Again, the maximum nominal voltage. The maximum, if it's 6 kV, then generate 6 kV. If you want, as we mentioned before, go 2, 4, 6 or 1, 2, 4, 6 and see if it changes a lot, but don't go more than nominal voltage. When we say 12 kilovolt, we mean no need to go above 12 kilovolt, even if it's an extra high voltage transformer, but you will always go lower, or you will always go nominal and not much higher than the nominal voltage. Mr. Pablo, hi, one question. For a complex transformer like PV transformer, double winding out, but with an electrostatic screen between the high voltage and low voltage windings, how do you suggest to do the test? Does it have sense to measure separately low voltage windings with a single high voltage and electrostatic screen, vector groups D, Y11, Y11? Thanks a lot. Mr. Pablo, we would need to have a little bit more information for this. If you could send me to my email, then I can check with some of our experts, because with electrostatic screen, I mean, normally you would short circuit the primary and the secondary side, but if you have electrostatic screen, I'm not sure how this impedes with that idea. So if you can send us more information, I'll try to see if we can get more information for you. Mr. Kelvin, so again, he's asking, what are the advantages of testing the insulation of a transformer using the TDX over using a conventional ground tester with a function for performing an insulation test? Well, I would say that with a TDX, you really get the tan delta value. And I'm not sure what do the other devices using the ground, like the ground tester, actually measure, but they don't measure tan delta. I mean, with the ground tester, you test if the grounding connection is okay, and with tan delta, yes, you do measure current running from the ground, but these are two separate tests. So please, better to do use the TDX 5000 to do this measurement. Mr. Harit Al-Shamsi, how frequent tan delta tests can be done? As frequent as you like. There are no limitations on that. Once a year would be good. Once every 2 years would be also not bad. Minimum once every 5 years. And I think we've reached all of our questions. We've answered most of them. I hope you had a chance to understand, to get some new knowledge today. My email you can find here. And also, if you go to www.altanova-group.com, you can find our regional offices and our local distributors. Feel free to contact them and ask for further explanations, or you can contact me and ask for further explanations to tell you what we know about tan delta and other topics. I call you to be present also next week on Tuesday to be with me when we talk about more detailed aspects of tan delta. Hope you had a good time, and I wish you a beautiful remainder of the day. Thank you for your attention. Bye.